Good afternoon, everyone, to this final session of the International Conference on Nanotechnology Research and Innovation. So, in this afternoon session, we have several keynote presentations. We will start with the plenary talk, and then we will have some oral presentations. So, our first speaker is Dr. D. Pukazhselvan. He's from Department of Mechanical Engineering from the TEMA Center for Mechanical Technology and Automation, University of Aveiro, Portugal. And he will be talking about promising multifunctional characteristics of magnesium hydride for energy storage applications. Dr. Pugal, the floor is yours.
Thank you, Dr. Anurag. Actually, my throat is not good. I'm in a recovery phase from a flu, but still I will try to manage. I hope I will not bother you much by coughing in between. But anyway, I have some remedies, water and these medicines to chew in case of urgencies.
No
All right,
problem.
okay, let us go ahead with the discussion. This is the topic of our discussion today. Promising multifunctional characteristics of magnesium hydride for clean energy storage applications. This material, magnesium hydride, is a popular material for hydrogen storage applications. But now it is also getting clear that this material can be used for several other applications. That's why they were multifunctional. Multifunctional means a material can be used for various applications. For example, titanium dioxide is a multifunctional material. You know that it's a popular photocatalytic material, and it has healthcare applications. It has some purification applications, pollutant removal applications, so on and so forth. You have it in our toothpaste, you have it in our paints, so on. Likewise, another example, if I can say, carbon is a multifunctional material. It can make you a human flesh, as well as it can make wooden frame. Okay, wherever it is required, what kind of functioning is required, accordingly it does. So that's the greatness of multifunctional materials. In that category, magnesium hydride. Okay, there is another word I am projecting: clean energy storage applications. What is that clean energy, and why clean energy needs to be stored? Obviously, every one of you know that. Nevertheless, to have a good beginning and to refresh with your memory, let's go ahead with these slides. For example, assume that all the way suddenly tomorrow our energy supply stops. It would not happen, but we have to be prepared for this because the worst thing is coming in few decades. Okay, at that time, what can we do? We need to counterbalance anyway the hydrocarbon-based economy, whatever it is providing us now. We have to take our life ahead with alternate energy infrastructure. What are our options? What are our options? Here are the options. Some are the most common renewable energy production possibilities, like solar, hydropower, geothermal, wind. You know that. It's most common. And some are less common: tidal energy, salinity gradient energy. We also say that RED, reverse electrodialysis method. And we need to expand the infrastructure of all these things, and along with some spirited use of nuclear energy. It all together with expanded infrastructure should be okay. But one point we need to note is that what all these energy systems produce is electricity, right? That electricity can be transmitted, of course, through grid lines, and intercity transfer or country to country transfer is also possible. By the way, you can power your houses, you can power your industries. In some cases, for transport applications, locomotives can be powered as well. These days, the bullet trains and all these things can be powered. Okay, but that would not be sufficient because the emission among the 100% of total emission, almost 72% emission comes from your cars, bikes, and other transport options, light and some heavy duty vehicles. So there, what you need is a portable medium. It's not, you cannot transmit like this directly to a moving bike, to a moving car. You need energy stored inside on board. So we need energy storage mediums. What kind of energy storage mediums we are looking for? What kind of storable energy? It has to be clean. Therefore, three popular means of clean energy we are projecting. These are hydrogen, heat, and electricity. Of course, others may argue ammonia and these things. Some few other fuels also can be synthetic hydrocarbon fuels, can also be the options. But okay, that is supplementary options. The most important are these hydrogen, heat, and electricity. How does it work? Yeah, simple flow chart. I will tell you what all these things so that you will understand the story clearly. Hydrogen. First of all, you need to produce it. The popular means of producing hydrogen is electrolysis, and then it's a buoyant gas that we need to remember. And immediately after that, you need to store it. A storage medium is required. And after that, the stored hydrogen can be utilized in a fuel cell to repurpose it, and you can run your car or IC engines that also can do it. And what about heat? Heat needs to be received, obviously. It's a form of energy that needs to be received. The most popular form of receiving heat is through solar concentrators, and that needs to be stored because it is something having escaping tendency. It can easily dissipate, okay? So you need a storage medium. And after that, the stored heat can be repurposed, for example, through steam generators that can provide you electric energy again. This promising way of doing this hydrogen heat. And electricity, of course, you know that we have been doing it. It's very popular these days. You have your cars, electric cars. The most popular means of producing alternate electricity, clean electricity is through solar panels, and then you store it on batteries and utilize it. So all the ways, the storage is very, very important. Without a breakthrough in storage, this cannot move ahead. Then the question is, to store all these three forms of energy, do we have a better material? Can we use one interesting material that can be utilized for storing all these three forms of energy? Then we will have economic benefits as well. We need not to develop individual material for individual purposes, right? Therefore, we have been looking for these kind of materials. One material, it is very majestic, is magnesium nitride. How? I will tell you. I will take some time in this slide to put correct things about how these stores these three forms of energy. Hydrogen, first of all. Magnesium's valence is 2. So with these two valence electrons, it can make two polar covalent bonds with hydrogen. So MgH2 can provide you a capacity of 7.68%, which is higher than the vehicle target. Hydrogen vehicle target 6.58% is the maximum target. One should not be scared of this one. What is this number? It is basically when your system has a capacity 6.58% or greater, that means your vehicle, hydrogen vehicle, has a existing gasoline equivalents of the vehicles. Okay, I mean whatever the existing gasoline vehicles can run, whatever distance it can run, the same performance can be reached. So if the capacity is higher, that is good. So is the material magnesium nitride for hydrogen storage. Okay, that is one thing. And second thing, how about heat? It is also quite interesting. When magnesium hydride absorbs hydrogen, it exothermically reacts. That means it adds up some quantity of heat to the environment. By losing this much amount of heat from the system, it adds up to the environment. And during the reverse reaction, during the discharge reaction, and it withdraws this much of amount, absorbs this much of heat. So it does cycle by cycle. I mean, during the charging, it releases, and during discharge, it takes that, adds up, withdraws, adds up, withdraws. This way, the quantity of heat that is stored, I think I need to take this point. That's why I was searching where has it gone. So I didn't put it yet. Okay. The quantity of heat involved in 1 kilogram of magnesium nitride is 2,850 kilojoule. It's a huge amount. And if to operate a steam generator, 1 kV steam generator, it's possible 15 minutes you can do it with this quantity of heat. It's promising. It stores hydrogen as well as heat. And what about electricity now? Magnesium hydride. For that, first of all, you need to understand the lithium-ion battery reaction involving graphite as anode active material. Graphite is the most popular material in the commercially available lithium-ion batteries, and its capacity is 374 milliampere per gram. Okay, that stores lithium through intercalation mechanism. Magnesium hydride in place of graphite can also involve electrochemically with lithium and stores several times higher quantity of electric energy. Because the reason is simple, because here 6 atoms involved for the storage of 6 carbon involved in the storage of 1 lithium. Here only 1 magnesium hydride involves in the storage of 2 lithium. So lithium by the active material ratio, that from that you will understand why this capacity is very high. So it's a very interesting thing, all these things magnesium hydride does. So this is one material we need to take very seriously. And the next question is, okay, this is a promising material. Do we have sufficient availability of this material? And how do we synthesize these materials in the laboratory? That's the next question. So let's see what's the abundance of this material, leaving oxygen and the silicon, which these two are the most abundant materials. And the next abundant series of materials are given here among the magnesium. And you would be surprised to know that magnesium is as abundant as sodium. Sodium you would see in ocean salt water, likewise magnesium also. How? Because magnesium, and in our earth crust we have lot and lot of magnesium rocks, big pieces of magnesium rocks and mountains. From that you will get magnesium, and then you can crush them into Mg granules, and in the laboratory you will convert it into magnesium hydride through the activation treatments. This is a bit challenging, but challenging in the sense that getting 100% pure magnesium hydride is challenging. Industrially procured magnesium hydride is something around 95%, 93-95%. So we solved this synthesis issue recently. First of all, you need to make an activation treatment that converts 5.3% of magnesium to magnesium hydride. Then comes is a deep hydrogenation step that makes 5.3 to 93% conversion. So the industries, I think most of the industries only sell these kind of materials. And then the third challenging step is to hydrogenate the residual materials, and that we have solved this issue recently. The steps are here. Okay, I will not discuss deeply inside of what all the procedures, but this is a story behind it. Okay, now once you produce your material, let it be magnesium hydride or whatever hydrogen storage material, the next question is, at what temperature this material would work? Is the temperature closer to 100 or 200, is it sufficient to do it? We need to check it. Okay, for that what we do is a scanning, thermal scanning of the material, either by temperature program distortion or by differential scanning calorimetry or whatever. Okay, in our laboratory we utilize differential scanning calorimetry. As you can see that the pure material, pure magnesium hydride discharges endothermically discharges hydrogen almost closer to 400 degrees centigrade, 375 is onset temperature, but it's a very higher temperature. What is the temperature at which our gasoline vehicles operate? It's room temperature. Gasoline is obviously a chemical. It combusts at room temperature. So anyway, for a chemical to react, you need a temperature. This way, if this chemical shows the temperature of 400 degrees centigrade, what is offered for our vehicles? So the question is, what is next? The next is, we need to reduce the dehydrogenation temperature of the system if we ever need to imagine about utilizing this material for vehicular applications. Then how do we do it? By catalytic approaches. we need to find the appropriate catalyst that can reduce the dehydrogenation temperature of the system. And several catalysts are there. I will tell one example. All right. We have utilized titanium dioxide, and that is why, as a multifunctional material, I took the example of titanium dioxide in the first slide itself. It's a very, very good material for various applications. Okay. A 3-weight percentage of titanium dioxide was incorporated with magnesium nitrate through mechanical milling treatment, and the experiments were done then under identical conditions. Then what happened? You see this in the results. The dehydrogenation temperature decreased dramatically, almost 100 degrees centigrade, even more than 100 degrees centigrade is there. It's very interesting. That gives you tremendous economic benefits. All right. Once we identify this, the next question is the quantification of hydrogen. How much quantity of hydrogen it provides. So anyway, look, this is a temperature closer to 300 to 350, say. At this temperature, I can operate this system. So I choose appropriate temperature, okay, under isothermal condition, that means constant temperature. Now I would evaluate how much quantity of hydrogen is released. The black one is the first cycle. It means the as prepared material. Well, very good. It's really good. That provides a capacity closer to 6%. But what is interesting is when you repeatedly do it, the kinetics and capacity both increases. In 5 cycles, it reaches a maximum, and after that, it stays. What does it suggest? It suggests that there could be a chemical reaction between titanium dioxide and magnesium hydride that might have produced an active species. That active species promotes further cycles. If nothing happens, because we started with nanomaterials, okay, if nothing happens, the cyclic curve should be one over the other. There is no reason to improve, okay. So there is the role of active species. We need to find what active species is that. If we find that active species, the next time we will not need to start from titanium dioxide. Instead, we will go ahead with the active species. Why unnecessary steps in between? It will reduce the processing steps and also the efforts and the energy investments, so on. Okay, so that we need to find what active species is this. All right. How do we do it? How do we find the active species? There are several techniques. Different research groups utilize different methods, whatever is convenient for them with respect to the facilities available. And for us, in situ X-ray diffraction was very informative. As you can see, this profile, the black one is a catalyzed sample. You see titanium dioxide is here, and it is titanium dioxide. Okay, now we are thermally decomposing this material. While you thermally decompose, titanium dioxide disappear. That means this is chemically reacting. And all other phases, we evaluate carefully what all these, and there is nothing surprising because magnesium hydride transformed to magnesium, that is fine. But what is surprising is the moment titanium dioxide disappears, another very interesting phase is forming. Sorry. Another interesting phase is forming. That is later on identified to be titanium dissolved magnesium oxide rock salt. This is the active species. And once we identify, there are several other investigations, all I am not showing. This is then identified as an active species. After that, we made a ex situ synthesis of this active species and started using this as an additive for magnesium hydride and tried to see what is the performance of this material. Obviously, it's as better as titanium dioxide or even slightly better than titanium dioxide. So this active species. This is not quite good. We would have expected that dehydrogenation almost around 240, or say, for example, for instance, it would have been very exciting, but this is how it is. But the story is that there can be several active species, but when you change the transition metal and repeat these measurements, and you can find out what can be the universally best active species among whatever materials available in the periodic table. If you identify that, you will solve this issue for the betterment of humanity forever. So that's the thing. That's the importance of these kind of works. I tell you pictorially, here is a periodic table. You at least have 30 transition metals. From that you can have this many oxides. It's in my collections, from whatever I know, but there can be some oxides I missed out. And also there can be several oxides. I'm a ternary oxide. By mixing two different oxides, there can be so many oxides can be formed. And from that, you can identify what can be the best active species. We really need to identify it. Titanium dioxide is the one. The work is already accomplished, and the others are highlighted. These ones, the highlighted ones, partial works are done, and plenty of things and can be done. Look, so many oxides and plenty of challenges. So many possibilities for doing research in this direction, and it's an unending research. Okay. That's one thing. Multifunction. Now, let us go back to the word multifunction. Why I say the word multifunction. Hydrogen storage is over. Now the discussion. Let us go on to the batteries. What all the characteristics. Let me recall this. How magnesium hydride can be straight away involved as a material for storing electricity. Here, lithium-ion battery reaction, I said in the first slide or the second, third slide itself. Graphite as an anode active material provides you capacity 374 milliampere per gram, and magnesium hydride in that place does 2038 milliampere per gram. Oh, then if it is great, why don't you use it? Let's go ahead with that. If something is promising, then why don't we use it? There are challenges exist. When nature provides you something amazing like this, and that also provides you some challenges that we have to come across, and we have to solve this. Okay, what are the challenges? Challenges are poor conversion efficiency. Although this is thermodynamically permissible, feasible reaction, the conversion efficiency is poor. And the reversibility is very, very poor. Okay, for both forward and reverse conversions. And what has to be done? And how to approach this issue. Okay, before that, we need to go through this. The forward conversion reaction is expected at the potential around 0.25 voltage. Okay, and the reverse conversion is expected for this material at 0.7 voltage. And if you get a deflection in your curve with these potential regions, then you will be very happy. Okay, when you are using clean magnesium hydride, let it be even 100% pure sample. And that sample, when you are using as an anode active material in a lithium-ion battery, provides you capacity just around 700 milliampere per gram, which is very, very less, right? Almost only 1/3 of the capacity. And what about the reverse conversion? You need to have the conversion at 0.7 voltage and anything. And no, the curve is going to heaven. It's going, and there is no changes. And the further cycles also decreases, and there is no reverse conversion at all. Then again, we have to call upon the help of activators, catalysts. Okay, we have used an interesting catalyst, chromium trioxide in a 5.8% concentration, and experiments were repeated under identical conditions. So, and what happened? And this one happened. The forward conversion almost closer to the theoretical capacity is reached. And what about the reverse conversion? Reverse conversion happens, and you have the reverse conversion almost closer to the potential which is suggested theoretically, and you do have it, but not fully, only partially. And in the further cycles, it decreases again. Yeah, at a particular state, in 5 cycles, the battery is dead. So that's a problem. And once it is dead, we need to know what is that, what is the cause of death. For that, we do a postmortem. It's like if there is an unnatural death, human life, what we will do. It should not happen. I'm sorry to take a human example. But anyway, that's the reality. That what we do is a post-mortem, right? What is the cause of death we see? The same thing in the batteries also. We just break the batteries, whatever by using which we assemble the battery, we want to take it out. And we break the battery inside the controlled atmosphere, which is glove box. And in our case, it is anode. We take out and laminate it thoroughly so that when you take it out absolutely outside of the glove box, it will not oxidize. And then we do it. By the way, it is a sorry. By the way, it is a Kapton film. Okay, it's X-ray amorphous film. It only gives you the characteristics of the sample. All right. What we have observed, what is the test result? The green one is the fresh sample, and different conditions we have tested, and what we identified is that at the intermediate stage, there is a alloy phase, lithium magnesium alloy phase, that refuses to convert again to the end material. We are stuck with that, and we need to identify the strategies to break this alloy and convert again to the end material. A partial conversion is there, but not full conversion. But in the literature, people are suggesting promising ideas, and we are trying to do our own approaches. And this way, slowly, we are getting into the reversibility, as much as reversibility as possible. And this line of research also is very, very promising. And then anyway, the next question is, can you have, by making any kind of strategies, can you improve the cycles? So for that, I have another example. Let's close this now. Another example. Anyway, I said magnesium hydride is a multifunctional material. How multifunctionally is this material? Well, this throat. Okay. Magnesium hydride, as you know, that it is also a reducing agent. Any hydride can be a reducing agent. And so magnesium hydride can be utilized for making promising hybrid structures and end up in breakthrough materials for energy storage. Such a breakthrough was obtained. I cannot say it is at the moment breakthrough, but a good performance is observed in our laboratory. For understanding this, I want to take your attention to this graphitic structure. It's a pictorial representation. When you use graphite as anode active material for a lithium-ion battery, what actually happens is lithium intercalates in between the layers. Okay, and the interplanar spacing required for the intercalation of lithium is 3.35 Armstrong unit as far as the graphitic structure is concerned, and that is there. The distance is sufficient. But the same thing is not true for sodium. It is a heavier, bulky atom and ion as compared to lithium. So there will be a very, very strong steric physical impedance that does not allow it to pass on. So what can be done? Imagine that we can slightly expand this interplanar spacing. Likewise, by making some kind of spacer in between, or by making some kind of pillar in between. It's only for a representative purpose. Okay, it's not a real structure. A kind of pillared structure is required to expand the interplanar spacing slightly, not too much. If you expand too much, there will be no intercalation phenomena at all. So this is the story. This is asking thing. And then our attention gone to graphene oxide, because graphene oxide is one of the most promising naturally exists. It's not a natural material, but naturally, whatever artificial material synthesized in the laboratory, graphene oxide is a good intercalation. Good pillared structured material. Okay. But its interplanar spacing is 8.2 Armstrong unit. Is very high. And also, the planes are too much crowded with several functional attachments, and that will not give sufficient space for the intercalation of either sodium or lithium. So what you have to do is you have to eliminate these functional attachments, and therefore it can come closer. Okay, it should not end up with graphene, but at least reduced graphene oxide. So some functional attachments can be there, and you need to get an expanded space. So our idea is magnesium nitride is a solid state material, and it's a reducing agent. Our idea is to attack these functional attachments. It's a vertical view, okay? I'm going to attack some of these functional attachments by magnesium hydride. I will make a redox reaction. Magnesium hydride reduces these functional attachments, and by the way, if it gets oxidized, and it can get stuck between as a layered as a pillar, and can make this kind of thing. Can I do it? It's a kind of presumption at the moment with logical assumptions, but can we do it? Do we end up with that? There's doubt, but still why don't we give it a try to this? And we proceeded in this approach, and what all the things we observed. And we made a composition, graphene oxide plus 10 weight percentage Mg. Come on, 10 weight percentage MgH2. Sorry, few seconds. Okay, we also use this type of materials for hydrogen storage, so we know how to play with these compositions. That's how this particular composition was chosen. Okay, and firstly, after making this composition, we wanted to test the individual components of it. How magnesium hydride alone would respond to the reaction condition that we are applying, how graphene oxide would respond, and then the entire composite material altogether. Magnesium hydride, the blue profile, okay? 5 milled magnesium hydride that endothermically releases hydrogen almost around 350, right? Fine. And what about graphene oxide? That reacts at around 200 degrees centigrade. The reaction is exothermic. So when you mix graphene oxide and magnesium hydride, if there is absolutely no reaction, you would expect 2 steps, one exothermic and one endothermic step, and no changes in the dehydrogenation or the transfer phenomena. But what we are observing is that one-step reaction at a slightly lesser temperature. That means it is an interesting chemical reaction between that. What chemical reaction is that? And that we are interested. And some series of tests were done. Firstly, X-ray diffraction. Graphene oxide at the X-ray diffraction proved that graphene oxide transformed to reduced graphene oxide. Exactly, that's what we were looking for. And we also wanted magnesium oxide because it has to go through redox phenomena. Magnesium hydride, some magnesium hydride transforms to magnesium oxide. And FTIR spectral investigations further proves that there were a lot of functional attachments initially, and most of them disappears, but still functional attachments are there. This is what we wanted as well. And the Raman spectra further proves that the defect band intensity significantly increases as compared to the graphitic band intensity. It's a clear sign that we have to call it reduced graphene oxide. MgO is there as well. So the proof of concept is made now. Graphene oxide to MgH2, the presence is this RgO, MgO. And what kind of presence is that? Basically, the assumption was this. If it's so, we are happy. Anyway, you need expanded interplanar spacing. And XPS investigations further proven that you have magnesium carbon bonding along with magnesium oxygen bonding that was proven previously. And graphitic nature is there, CC. And pi overshoot says that it can be a layered structure and functional attachments are still there. So it's all giving more and more values to our assumption that something interesting pillared structure like that may happen. It may not be a perfect structure that as we assume, but at least some pillaring activity could have been there, right? And electron microscopy investigations, as you see, this is the graphene oxide, the starting material, and here is the end material. Clearly, as a visual representation, what it suggests, you clearly can see that it's still a sheet-like structure. but something is deeply buried inside. It's a coagulated existence. Something is embedded deeply. That's what it says. And see the high resolution planar view of this, how it is. You can see the changes, right? And then one another investigation is scanning, chemical scanning in the high resolution. Just our interest is to know how well localized these ingredients of this structure. Magnesium, oxygen, and carbon. You see, very well localized. There is no separate patches or islands. Okay, that clearly suggests that this material can be a very composed version, atomic level composed version of something. That could be something like this, or something closer to that. This is what we were looking for. And then, right, you got the material and you would make the battery. Not only lithium ion battery, this time you would also make sodium ion battery and try to find out the performance of this material. Okay. A little bit of protocol. I want to tell you how do we make the battery. Those who are not familiar with the battery making. We take this much composition, 80% of active material, 10 weight percentage of binder, that is PVD weight, polyvinylidene difluoride. This is a standard binder, and 10% of conducting additive, which is carbon black. Okay, mix them well, add some NMP and methyl pyrrolidine to make it in the form of slurry, enlarge it on a current collector, which is copper in our case, and then reshape it into the anode form, circular disc. For CR2032 type configuration that you use, the batteries that use in wristwatches and in several other places, and small weighing machines, so on, these are the batteries. Okay, 1.2 centimeter is the diameter of this. You can customize it. Some use 1 centimeter, some use 1.4 centimeter as well, and we use 1.2 centimeter. These are the other components by using which we assemble the battery inside the glow box. And for sodium ion battery, you use the reference material sodium, and for lithium ion battery, you use lithium. Other components are same, and you need to carefully choose the electrolyte as well. For sodium ion battery, sodium conducting electrolyte, and for lithium ion battery, lithium conducting electrolyte. Okay, we are coming closer to the end of the presentation. Before that, I discuss some results, whatever we have observed. The first series is for lithium ion batteries. LIB means lithium ion battery, SIB means sodium ion battery. Okay, don't be confused of this thing. So protocol, firstly, when you do a battery testing, you need to test cyclic voltammetry. It's very informative, because cyclic voltammetry can tell you at what potential the insertion of the metal of your interest. In the case of lithium ion battery, it's lithium insertion happens, and at what potential extraction happens, and whether this process is a recurrent process or not. If it is a recurring process, it is a rechargeable battery. If not, it is not a rechargeable battery. And what about the current response? And what is happening? What kind of electrochemical event is happening at what potential range? These all the informations can be explored from that. The history of the material can be predicted. So by looking at the cyclic voltammetry, we feel that it's a very good rechargeable battery. And then the charge discharge profiles were evaluated. As you can see, that very good consistency, the capacity closer to 500 milliampere per gram. Remember that graphite, natural graphite, 374 is the theoretical capacity, but experimentally you end up between 200 to 300. And now you have very good capacity with consistency, right? And the third important test is rate retention analysis. Or something is hiding, rate retention analysis, in which what we do is firstly we test with the smaller current density, in this case 100 milliampere per gram. Okay, and then slowly you increase the load, that means increase the current density and reach a maximum current density. Okay, when you give more and more load to your battery, obviously the capacity it settles between the electrodes will be different. I mean, it decreases. Okay, and the important thing is that when you go back, when you systematically reduce step by step the current density, it has retained the capacity it was before. The best battery does it. Okay, so by seeing this, you can understand that this is a very good battery, really a good battery. And what about sodium ion battery? Remember that sodium ion battery cannot be made with graphite because the intercalation, the interplanar spacing is not sufficient for the intercalation of sodium. But here what you see is a recurring process. Really it is making reversible battery, recyclable, rechargeable battery with the sodium. And we have been looking for the replacement of lithium in the battery applications. Okay, we need to come with a breakthrough in developing sodium ion batteries as compatible as, as good as lithium ion battery. So this one, capacity is a little less, that is expected because sodium is heavy, it is expected. And the consistency seems to be quite nice with this as well. And the capacity seems to be very nice again. And the rate retention profile also says that this can as well is a very good battery, right? And the next one, cyclic test. How long this cycle can go? So in two different current densities, we have tested for both. One with a smaller current density, 200 milliampere per gram, almost never, for all the materials I do in our laboratory like this. One smaller current density, one higher current density, so that we can compare at a particular stage what material behaved how. Okay, for these ones, lithium ion battery and sodium ion battery in a smaller current density, absolute consistency quite good, up to 300 cycles. And what about high current density charge discharging? This was done up to 3000 cycles, and it's very good as well, except a slight performance decay there in the case of lithium ion battery, but not very much. Look at 30,000 cycles. 30,000 cycle means if you assume the battery, whatever you are using in your cars or even wristwatches or your laptops, assume that you charge it once in a day. That means once in a day means 3,000 cycles, almost closer to 8 years or what? 8 years and 2-3 months, right? And these days, the companies provides you 5 years of guarantee for a battery, and here already it gives you 8 years in a rough sense. Yeah, it can even go further 8 years. So likewise, these kind of alternate battery making and trying to identify the proper suitable material and look at things in the atomic levels and improve things will be very beneficial for reaching a breakthrough in energy research. Okay, and these all the things not only we do, all across the world scientists are trying hard for it, and we all together can do wonders. When a critical condition comes, we will not have any hydrocarbon fuels at all. We'll go ahead with these. We are confident. And the final one, the post-mortem investigation was done as well, and because it's a protocol. we break the battery and try to identify what happened after some cycles, whether the surface is okay or not, the cross section is okay or not, and any rough patches are there, any dendrite formation is there or what. All these things needs to be done. Firstly, the fresh electrode and then the cycled electrode. Okay, the fresh electrode says that firstly it is a bit porous and stacked sheets of active material, and that's what is expected because graphene oxide, reduced graphene oxide with the pillared structure is expected to be like this, the cross section suggested. And after several cycles, these are all filled because it's expected as well because of the intrusion of the electrolyte traces. Lithium ion battery, sodium ion battery, almost both are same. There is no anything untoward or surprising, right? Everything is normal. And your investigation tells, yes, this is good as well. There are several functional attachments after cycles. This is because of the electrolyte traces, because organic electrolyte traces and several things will come. And main interest is that how fares these magnesium oxide bonds, whether it is existing there or not. A slight, maybe some perturbation in the case of lithium ion battery we observe, but still it is the pillar structure remains, and that's a good news. So good structures, and the result producing structures like this needs to be synthesized in the laboratory to reach a level, to reach a breakthrough in energy research. Okay, with that, let me conclude. I think closer to the time, maybe a little over,
Slightly over.
yeah, slightly over. I'm sorry because in between we had a pause as well. So the conclusion is that magnesium nitride is a promising multifunctional material, and for hydrogen storage, it is quite successful. And when you use magnesium nitride as anode active materials right away, cyclic stability is not good. But when you use this material for making hybrid structures, the cyclic stability is very, very good. The last previous slides said it. Okay. And I thank the funding agencies, thanking you all. Here you can see the funding agencies with the logos, what all the funding agencies involved instead of reading all this text. Thank you. Also, I
Yeah.
thank my throat, but not for not giving much troubles. Okay.
Okay. Thanks a lot, Dr. Fugal, for this very inspiring presentation.
Yeah.
So if
Thank you.
anybody have any questions, the floor is open for comments, questions, discussion. Very short, 1 minute.
We already crossed the time. I'm sorry for that.
No problem. So if nobody is asking, I have one question
Yes.
regarding your titanium as the catalyst. So
Yeah.
first you added the titanium oxide, right,
Yes,
as the
exactly.
catalyst, and afterwards, instead of titanium oxide, you decided to add titanium
Active species which is
you
generated.
have magnesium titanate. You added some kind of a magnesium
Yes,
titanate.
exactly.
And like, do you have to like synthesize this material, or is it like
Yeah,
already there?
Xe2 synthesize this material.
Okay.
We know what is the exact concentration that we need to develop, that we need to employ, and what kind of milling conditions required for it.
Okay.
And these are pre-optimized by testing various concentrations. I showed you only one concentration, but when we want to have the Xe2 synthesis, we really need to work on several compositions and come up with one best composition that actually end up with this.
Okay, so in this case, like you know the X and Y amounts, right? Or is it like you're still
Yeah,
not aware
X
of
and
it?
Y amount I know, but
Okay,
here I decided to put only XY because there are several compositions. Okay,
okay, okay,
several compositions also lead this structure, but the one what I used is 2:1. Okay,
okay,
magnesium hydride 2:2 molar ratio, and titanium dioxide is 1. For example, if I use 4:1 and 3:1, that also provides this. But the temperature reduction was not that good. It was so closer to this one only. I mean, the original one only. It was, and the observation was like that.
okay, great.
Yeah.
Okay, so if nobody has any more questions,
I
so
have,
I
I
think
have,
because
I
of
have,
the yeah,
There you
please,
go.
please.
The convener,
I
the
have a
boss.
Yeah,
general question. Thank you very much, Pukash, for your presentation.
Pleasure,
I, I,
Igor.
I have a general question as specialist in this area. What is your opinion for future? We reach maximum capacitance for lithium battery, or what is situation now in general? What is your
Promising.
opinion?
Igor, it's really promising. Promising materials are being reported routinely. As far as the anodes are concerned, it is really promising, but some little bit of setbacks are there in the cathodes. Only anodes cannot provide you breakthrough. You also need better cathodes to counterbalance this performance, but costs are being reported. And I'm sure that at least 2 to 3 times capacity improvement is possible.
No,
And
two, it is good, yes.
yeah,
Yes, this
if
is
you
good.
increase the
If it's
capacity
two,
three
to two,
times,
two
you
times,
go.
yes, it is good. Yes. But
Yeah,
this is,
if you improve the performance of capacity of the material 3 times, that is a strike, meaning that your vehicle will run 3 times. Instead of 100 kilometers, it will go for 300 kilometers. Ah,
yes,
this
yes,
is
yes,
really a promising area.
yes. Okay, okay, thank you.
Yeah.
so because of the time, we have to end this. I also have more questions, but I will ask you later on.
Yes,
So
today we will have a dinner. At that time, you can ask. Um,
yeah,
um, Anurag, I'm sorry for taking a little bit extra time. Okay, I'm sorry. Okay.
no problem, no problem.
Okay.
Thank you once again for the nice presentation.